Okay, welcome to the fourth class meeting of EECE341, Introduction to Communication Systems. As I just told you, please regularly check your attendance at this webpage, rollbook.postec.ac.kr. As I told you, I'm very generous in your unexcused absence. However, according to the school regulation, if your class absence is not more than 3/4, then I have to give you fail to this course. Whatever score, whatever highest score you get in the final exam, midterm exam, or something. Got it? Announcements on homework, quiz, exam, and voluntary project. As I already told you, you'd better download a handout for chapter 2, and its password is lowercase TWO. And homework 3 is assigned as you all received my short message. It's due on this Friday, 9:30, so you don't have enough time. One of the reasons why I push you is that as the Eastern Asian proverb says, the start is the half of the way. So please start quickly. Got it? And then, just a second. No, there's some noise. And then homework 4 will be assigned probably by this Friday, and it's due on the Monday when you return from the Chuseok break. On that Monday, we will immediately start our first quiz on signal gen systems, which is the prerequisite material. So prerequisite means that you cannot take this course without having taken that course, which means that your knowledge on that subject is mandatory. So you will have quiz 1, and first you have to be able to access PLMS system because problem set will be available from the web page, and also you have to punch in or upload your PDF file as quickly as possible on the PLMS so that I can be free from the burden of keeping your answer books for 5 years or 10 years. Got it? So be well prepared. And also, it's an open everything quiz except any human interactions. You cannot post the problem on some web page and ask mass intelligence to solve it. That's not allowed. Got it? However, you can use LLMs if you want. ChatGPT, Gemini, Bing, anything. However, I guarantee that those answers you got from the LLMs are incorrect answers. I intentionally select those problems. So try to memorize a lot of important equations so that you can freely use the equation in solving the quiz problems. About voluntary project, this is very tricky thing, but I will talk about that after the first midterm. By the way, in the last page of the first chapter handout, I put a page that is related to one of my the most important message through entire my education, my teaching. Not only this course, but also for every course, including graduate courses and something. So let's read it very quickly. Where it is? Okay, just a second. So many of you, I believe, already know because many of you admired Albert Einstein, and you know the famous quotes of Einstein. And he once, or I don't know, it's just misbelief, but he told, and other also famous people told something like this: everything should be made as simple as possible, but not simple. Which means that in order to understand some problem, simplify. In order to solve some problem, try to simplify. And you had better or practice this how to say it, this approach from now on, or probably you've already have been doing this when you are a middle school student or even elementary school student. Whenever you confront a new problem, probably some apparently looking difficult problems are looking difficult because it's simply new. So what you do is that you divide the problem into smaller sections and try to understand each section. If you don't understand, even after dividing it and try to conquer, what do? You simplify the problem. So you make the sub-problem as simple as possible, but still keeping the essence of the problem. So here, simplify requires keep the essence of the problem. Okay. So keep the essence of the problem. Sometimes there are essences. You take out some essences, but try to keep most important essence. And suddenly, the problem looks very simple to understand, and even you can solve it. Then what do? You complexify by adding those you have taken out. And then suddenly, since due to your experience in solving the simplified problem, suddenly you can solve original sub-problem. And you do this tactic for every sections you divided, and then you try to integrate them, and you solve the entire problem. And you must do something further. You try to generalize the problem. So your given problem was this one, and you divided it into smaller sections, and even some smaller sections couldn't be understood easily. You simplify, so you divide further, or you transform, or you convert the problem and solve it, and then you understood and solved the original problem. And then what you do is that you consider something bigger, something more generalized one. So simplify does not only mean simplify, but also mean you generalize after you solve the problem, understand the problem. Got it? While you take this action, there goes another message, visualize. And visualize is actually not only claimed by me, but also the father of information theory, Claude Shannon, also talked about. Try to visualize. Of course, he also talked about simplification. So try to visualize what you are doing. Sometimes, as an electrical engineer, drawing block diagram is very, very useful. For example, some of you are taking undergraduate, some artificial intelligence course. And unfortunately, the theory is mostly developed by computer scientists and engineers, and they love graphs. So mostly there are edges and vertices, and we electrical engineers have difficulty to understand directly. However, if you convert that graph as a system into a block and consider, okay, here goes observation, and what we want to do is statistical inference, so we generate, for example, unknown parameters estimate. Then suddenly, you can understand what's going on. Another thing is, as you've already seen from my 3 class meetings, I love drawing Venn diagrams. Of course, strictly speaking, some people say that what we draw as Venn diagrams are Euler diagram, but anyway, I cannot distinguish or differentiate Euler diagram and Venn diagram, but I love Venn diagrams. Sometimes Venn diagrams provide us what we handle, because we think everything as a member of some subset of a larger set. By thinking in that way, we can construct a hierarchy of concepts. And that gives us better understanding of what we already know. And it's similar to your dormitory room, especially the male students. If you open your drawer, everything are just cramped. And there is no space to put something new. However, if you classify your clothes and you fold them carefully, suddenly you have a space. Same thing happens in your brain. So probably some of you may say that, okay, I have been memorizing too much. I'm running out of DRAM in my brain, but actually it is not. If you compress your knowledge by keeping the essence and simplify everything, sometimes you memorize something very small, and whenever you want to expand, you can just generalize immediately to get the result. But to do that, sometimes this visualization method is very, very useful. So I've been talking about this simplification and visualization, the two messages, now for around 20 years in my teaching. And I received an email this year. He was an undergraduate advisee of me. He didn't join the graduate school. After the military service, he just joined some company. But he suddenly contacted me, and he had a blog here and wanted to share, wanted to put my name. And he said in this blog page like this. He remembered these two words, visualization and simplification. And he said that this guided him to become a so-called S-class engineer. So if you read his blog carefully, he got selected as a so-called S-class engineer, and the company decided to fund him for his graduate study abroad. He got admissions from many prestigious universities, those names you know, something like that. So it's not just my claim. Albert Einstein emphasized the power of simplification. Claude Shannon also supported the idea, simplification, and also supported the visualization method. So you try to make it a habit to use these two tools. As I told you, your undergraduate years are spent to fill your toolbox with useful tools. So it's like when you are admitted and you had the admission ceremony, you have vacant toolboxes distributed by post-tech. Let's think about that. How many new tools are now you are equipped? If you believe your toolbox is too spacious, then you must encourage yourself. Anyway, so this is one of the most important message. And last time, we talked about approximation of Maxwell's equations for circuits, electrical and electronic circuits. And I told you that our mathematical model for a current or even voltage may be a mere approximation. Because after the notion of current invented, we human beings eventually got that the electrical charges are quantized and electrons are the elementary particle. And even the quantum physics told us that the position and velocity of an electron cannot be deterministically given. In that case, the accumulated charge at time t as a function of time may be not a function of t. If we insist, precisely speaking, so suppose we know the position and velocity, then the q of t is a piecewise constant function. We cannot differentiate it without using direct delta functions. No smooth current can even imagine it. However, since there are a lot of electrons in our wire, if you just zoom out and vaguely just make your eyelid very closed, then it suddenly looks very smooth and differentiable. So what they do is that, okay, as far as the theory does not give us something strange, let's use this mathematical model. That is a function, real valued function of time that models current, voltage, and those things. However, quantum physics says that electron's position can be only described by what? So-called wave equation, or the probability density function. So if you become an engineer who do extreme electrical engineering, who have to rely on quantum physics, and you have to count the number of electrons, because, for example, your space probe to be communicated is too far away, then you have to rethink whether your model, mathematical model of current, voltage, or received signal, EM wave, is still applicable or not. You have to rethink. Got it? That was the message. And then I moved back to our well-known signals and systems field, and just, okay, from now on, I will use the time function. So I use a function x that has domain R and codomain R. So x is a function from R into R to model, for example, electrical signal. And we may have a graph So what is a graph of a function? Set of pairs, time t and its value, right? And here also I emphasize that this infinity and negative infinity are what must be interpreted as from the original time of our interest, past time enough, future time enough. So sometimes 1 millisecond could be interpreted as negative infinity, and 1 microsecond from now on could be interpreted as plus infinity. It does not, as mathematics says, it does not mean negative infinity time and positive infinity time. Something for sufficiently large. So sufficiently large. You will see a lot about this two-word phrase, sufficiently large or sufficiently small. Sometimes negative infinity may be told sufficiently small, or sometimes something like this. When limit t tends to 0, what does that mean? This limit interpretation must be interpreted as what? For sufficiently small t, right? So whenever you have limit, because this is also includes the concept of limit, try to interpret in engineering terms, like for sufficiently large, sufficiently small, sufficiently long ago, something like this is sufficiently long ago. Anyway, and then I draw a block diagram. So let's consider the set of all deterministic signals. So this is the set of all deterministic signals. And we have a very small subset, which is too small, so let me exaggerate. And this is a subset of what? Periodic signals. And I tried to perplex your definition of periodic signal by telling you that, okay, what is the definition of a periodic signal? What must be shown to say that X is a periodic signal? Do you remember the definition? A time function, a continuous time function X is periodic if what? Then what? You have to be able to state that one. And definitely, I can assure that 99% of you cannot fill up that part in English. Of course, you can do it in Korean. What does that mean? Even though you are well educated compared to other Korean electrical engineering students, you are very poor in precisely stating some concept compared to other electrical engineering students in, for example, United States. So who are the competitors? Not your friend next to you, those engineers. For example, in Indian Institute of Technology or Tsinghua University in Beijing. So what was the definition? Definition. X R into R is periodic. If. By the way, when we define something, if means if and only if. Got it? It's different from if in theorems and lemmas propositions. If they are not in definition, if means what? This direction. Okay? If blah blah satisfied, then something. However, in definition, you say some statement if this must be interpreted as if and only if. I understand. Some of you say that, what? I also did that. Even I realized that thing when I become a graduate student when I was taking the mathematical analysis. Anyway, if, then fill up. X is periodic if what? If there exists some t positive such that this S dot T dot means such that what? X of T equals X of T plus capital T for all T. Got it? So you must be able to fill up this black box part. And I may ask you to fill up in your quiz. Got it? Because I tested my son, who is also in electrical engineering department, not in our school, but in other universities. So I asked last night, fill up this part. And as I expected, he couldn't fill up. Got it? So it's okay. It seems that the Korean education is failing. So it's okay. Not okay, actually. Anyway, and then there goes another thing. In the above definition, T is called what? And fill up this part. T is called what? So you cannot simply complete a sentence, most of you. Me either when I was at your age, actually. But try to break out of that vicious cycle. Even after 30 years of Korean electrical engineering education, we are still not educating the Korean students as a top-level world-class students. I really am shameful, but you must encourage yourself. So fill up that part. And you may say that, period. Something still missing. So fill up an article. So which one? It's a period. Because any natural number multiple of this t can also be a period. Got it? So if a period exists, then it's not unique because it's any positive integer multiple is also a period. So it's a period. Now, in the above definitions, something is called the means unique fundamental period. So fill up these two boxes. Still, you can't do that. Something's wrong, right? So what? The smallest period. The smallest period is called the fundamental period if it exists. Okay? The smallest or the smallest period. Got it? So sometimes a periodic signal does not have a fundamental period. As I told you, a constant function, for example, x of t equals 1 for all t, then any positive real number is a period. And you know that no smallest positive real number exists. Got it? Of course, this is too precise definition. What we usually handle is not this, fortunately, but what? First thing is that, as I told you here, we think about a real valued sinusoidal signal, which is periodic. By the way, you may say that, oh, what happens when omega sub 0 equals 0? In that case, it's a constant, right? Still, it's okay. Anyway, that is periodic signal. So we started from sinusoidal signal, real valued sinusoidal signal or functions. And let me ask you the question. What is the fundamental period of this signal if omega 0 or omega naught is not 0? What is the fundamental period? Yeah, so you need to remember this one, right? So the fundamental period is 2 pi over omega 0. And as you immediately notice, you cannot divide by 0, which means that this definition or this approach only works for what? Non-zero omega 0. Right? And another thing is that in this course, even though these lecture notes use omega 0, I prefer using 2 pi f0 t plus theta. And here, what is the name of omega 0? That is called frequency in radian per second, or simply called radian frequency. However, this f now is called what? Per second, which means that it has the name of Hertz, Heinrich Hertz, who demonstrated the existence of electromagnetic wave, right? Heinrich Hertz. So I prefer using Hertz rather than radian per sec. Okay. Now, again, let me ask you a question. If this frequency of the real valued sinusoidal signal is not 0, what is the period? What is the fundamental period? 1 over f0. And as I told you, this has unit Hertz, but Hertz is same as per sec. So this has unit sec, and this has 1 over second. So the unit matches. By the way, this trick, whenever you see some physical quantity, first try to find out the units of each value is very, very useful. I didn't know this one, but when I was a freshman at the end of the first year, there was a senior in physics department in my amateur astronomy club. So he was writing his thesis. Some universities require graduation thesis even for undergraduates, but I'm not sure. Yeah, he was a senior in physics department, and he was doing some experiment in the lab. So I asked him to bring me to his lab, and we had some discussions. And he taught me to use this trick, focus on the units. And it seems that that is very useful. So I hope you can also use that. Okay. So whenever you write something abstract, especially not using some numbers, but the symbols, try to check whether your units make sense or not. Anyway, so real valued sinusoidal signals are very, very important. And now let's talk about Fourier series, especially real valued periodic signals Fourier series. So here we have. So suppose x of t is real valued. What does that mean? This is what? R into R, right? So this means real valued. If I say function x is from R into C, then it's complex valued, right? Suppose x of t is real valued and t0 is fundamental period, which means that this holds for all t. Now, what did you learn about this situation? Fourier series and periodic signal, real valued. And what you have is this one. X of t can be rewritten as a summation of what? Summation of what? Cosine functions and weighted cosine functions and sine functions whose periods are integer multiples of the fundamental period of this t0. But what you remember mostly is something strange like this. So this is what you remember from your signal gen systems. If x of t is periodic with fundamental period t0, then it can be written as summation of complex sinusoidal signals with period t0 over k. Got it? See that? This is periodic with period t, but it is also periodic with period t0 over k. Okay. Of course, for k0, it's constant, right? E to the 0 is 1. And also, you remember that if we assume it's real, something interesting happens. The case coefficient and negative case coefficient has some interesting relation. What? They are conjugate pairs. Remember that? This is called conjugate symmetry of Fourier coefficients for real periodic signals, real valued periodic signals, right? So you could find a table on the textbook filled up with more than 20 lines about the properties of Fourier coefficients, Fourier series coefficients. By the way, this strange conjugate symmetry holds if and only if X is real valued periodic signal. So if it is a complex valued periodic signal, you don't have, it's not necessary that you have conjugate symmetry of the Fourier coefficients. By the way, what is this one? This is summation of countably infinite functions. See that? This is what? This is a function of time t, right? Left-hand side is a function of time t, and right-hand side has sum of time functions of t. Got it? And these time functions are scaled by the coefficients called the Fourier coefficients. The problem is that we have how many functions do we have? We have, of course, in some times, these Fourier coefficients are mostly zeros, and only finite number of Fourier coefficients are non-zero. For example, x of t is cosine 2 pi t. Then what do you have? You have only two non-zero Fourier coefficients, right? In that case, that sum, apparently looking as countably infinite sum, is okay with no mathematical difficulty. However, sometimes, suppose you have square wave, then what happens? As you remember, you have countably infinite non-zero Fourier coefficients. In that case, you have to sum up those countably infinite functions of time. Then you have difficulty because this actually involves the limit operation. Limit n tends to infinity, summation k from negative infinity to, negative n to positive n. Then you have summoned, and you may call, if this right-hand side exists, you have the nth Fourier series approximation of the periodic function. Why do I have this one? Sorry, I'm sorry. Just a second. 방해 금지 모드가 자동으로 켜지게 해놨는데 안 되고 있네요. 아직도 안드로이드 폰에 익숙하지 않아요. 아이폰 쓰다가 바꿨는데 한 학기 됐는데 아직도 그래요. Okay, so let me see. I'm sorry. So if we drop this part, then it's called the Fourier series, nth order Fourier series approximation. But what does this mean? You think about the limit of this function. And unfortunately, many of you who are not doing mathematics minor or double major or something, you have no idea about the convergence of a sequence of functions. It's also a shame because when I was an undergraduate student in South Korea, there was at least one department, one electrical engineering department, or its name was not exactly electrical, but anyway, whose curriculum required every student to take mathematical analysis from the math department. Of course, most of the students got very low grade, but anyway, these days, students are not filling up their toolboxes with fundamental tools. It's very shameful. So anyway, you have to think about the convergence of the sequence of functions. And you remember something like Gibbs phenomenon. By the way, in Gibbs phenomenon, what is the name of the discoverer? Gibbs or Gibbs? Anybody? Gibbs is the last name. What was that? What was the Gibbs phenomenon? Gibbs phenomenon was something like this. Let's think about square wave, which is a periodic signal. And we find the Fourier series coefficients. And we construct a sequence of approximations by thinking about x1 over t that has 3 terms, right? DC term, the constant term, and first and negative first harmonic term, and x sub 2 over t, x sub 3 over t, xn over t, and let's plot the graph of these sequence of functions. Then what happened? In your undergraduate textbook, you've seen something like this. And saying that even though you increase this subscript n, still the amount of maximum overshoot and undershoot does not diminish. So the error, maximum error from the original square wave to this Fourier approximation does not diminish. It's still there. However, the energy of the error signal, so x of n of t, x of n of t minus x of t, and then you take the square and you integral for 1 period. Then interestingly, this energy of the error signal tends to 0 as you increase n, as n tends to infinity. Or if you want, limit n goes to infinity, this error signal's energy equals 0. But as I told you, you have to interpret this one as what? As what? This will definitely appear in your quiz. What? For sufficiently large n. Okay? You have to interpret limit n tends to infinity, this part, as an engineering term for sufficiently large n. So for sufficiently large n, the energy of the error signal is almost 0, okay? Or can be made arbitrarily small. Got it? So in some sense, even though the magnitude of maximum deviation from the true periodic signal does not diminish, it's okay. Its energy goes to 0, right? Because in our electrical circuit or electronic circuit, energy makes a difference, right? So why this happens, by the way? This happens because we use mathematical model, so-called time function, to describe our electrical signals. The problem is that this mathematical time function of time, has too much details. Some details we electrical engineers must ignore if we play within some boundary. Hey, forget about that limit. It's okay sometimes. However, your future, I don't know. You may be an extreme engineer who has to handle quantum mechanics. And also, you have to count the number of electrons to make your transistor very small, right? We want to increase the number of transistors in our cell phone, right? So nobody knows. In that case, our mathematical model, if you keep this model, you may have something strange, something unreasonable. However, you have to be an engineer who can distinguish whether your model fails or your reality really need that strange behavior. For example, because you are not familiar with that, but most of you know Stephen Hawking, right? The late Stephen Hawking, who was a very famous physicist, astrophysicist. And he studied the kind of physics of black hole. And you may say that the physics of black hole is related to the general relativity. When the mass is very large, some astronomical object has amazing size of mass. And there is so-called what? As the one of the famous, I also like the singer, the event horizon, right? You know, event horizon is formed around black hole. And what's the definition of event horizon? If some particle crosses over that boundary, it can never come out from the black hole, something like that, right? And Stephen Hawking was a very interesting person who tried to combine this theory of massive astronomical object with quantum physics. So he thought about that. Okay, as far as the temperature of the space near the event horizon is not 0 Kelvin, according to the particle physics, I don't know, I read some article. The energy in a very small scale becomes two particles, one with so-called, for example, you have an electron, then you have a positron, right? Antimatter and matter. And he thought about the case where when some space position just out of the event horizon just had the non-zero Kelvin, so two particles formed. Unfortunately, matter, for example, electron, crosses over the event horizon and disappears. Then what happened? That the positron, the antimatter remains, and eventually this antimatter will meet the matter around the black hole outside the event horizon. And what will happen? Matter and antimatter combines very, how to say it? Explosively and emits the energy, radiation. So he combined these two things and predicted that black hole is not black. Black hole will radiate something. And it was very interesting, right? So we thought black hole is black because everything is observed. But he combined these two extreme physics and predicted, actually not him, but a group of people, including Stephen Hawking, predicted black hole will radiate something. Not like our sun, but radiate some electromagnetic wave. And now, some people criticized those physicists' original research, saying that, well, event horizon may be derived from the general relativity. However, is it interpreted as a mathematical boundary? Think about three-dimensional space and a sphere. X squared plus y squared plus z squared equals r squared, the set of point x, y, z. Then you have a kind of imaginary three-dimensional space and a sphere with radius r. And you know exactly what is the boundary, surface of the sphere. However, that is just mathematical entity, right? Of course, you can divide the inside and outside of sphere, but it's pure mathematical something. But using that idea, okay, let's assume this model is mathematically correct, exact. Then what will happen? That was Stephen Hawking and his colleagues' approach. Sometimes that really works. Sometimes it fails. And your signals and systems model may fail if you do some other research, not communications. In communications engineering, even sometimes we change the order of limit and ignore what would be difference, because in most of the cases, those mathematical rigor is excessive, okay? However, in some cases, really this apparently excessive mathematical analysis gives us something very interesting and neat and beautiful. So if you want to major in, for example, especially control engineering, automatic control, then next semester, you find the mathematical analysis course in our math department and take it. Okay? That will change your life. For example, if you join some automatic control laboratory in our department, and professor just looks up your transcript and finds that you have taken mathematical analysis, immediately you may become his or her golden boy. Okay, you can do this prestigious research. However, if you are not well equipped, which means that your toolbox is not filled up with tools from mathematical analysis, he or she, professor, your advisor, may ask you to do something similar to senior design project forever while you do graduate study. So if you don't want to be a person who do the senior design project forever, well, educate yourself. Anyway, so here goes the results. If a periodic signal is real valued, then Fourier coefficients are conjugate symmetrical, and magnitudes or modulus of these complex coefficients are the same. The phase angles are other functions, something like that. There are a lot of properties. Now, what about this one? When do we have this Fourier series? When X is real valued periodic signal. See that here A, B are real valued. Okay, this is real valued. These are real valued. And we know cosine and sine functions with real valued arguments are real valued. Of course, X is also real, X0. So using that conjugate symmetry, we can always convert our original Fourier series using the complex exponential function like this. Using this property, we can convert it to cosine and sine functions like this. Got it? And even you can find integrating the original periodic signal times the harmonics of harmonic cosine and sine to get the coefficients for the cosine part and sine part. Now, one of your homework problem has some problem like this. So given x of t equals a cosine 2 pi t plus theta, find Fourier coefficients. In our textbook, it uses xn for Fourier coefficients. What do you do? Of course, you can use these formulas. So you put a cosine 2 pi t here and multiply sine and cosine, but never do this. Okay? If you do this, your 30 minutes will be wasted. So what you do is this one. Last time I emphasized the beauty of what? The Euler's identity. And of course, it's simplified version by substituting pi. We have the most beautiful equation claimed by Richard Feynman. However, what is the accompanying two equations? Real part of e to the j theta is cosine theta. And imaginary part of e to the j theta is sine theta. And also, if you generalize, what is real part of complex value z? How can you replace this one using some arithmetic operation? That is this one. What is imaginary part of z? That is z minus z conjugate divided by 2j. As I told you, I love using this j instead of I to represent the square root of -1. So here, what you do is simple. What is this one? This is real part of e to the j, fill up 2 pi t plus theta, right? Now, what is this one? Half e to the j 2 pi t plus theta plus e to the -j 2 pi t plus theta. Are you following me? See that? From here, you convert it to 8 times real part of e to the j argument. And then here, what you do is that you replace real part of something with something plus its complex conjugate divided by 2. These steps are most important steps in this course. Okay? If you cannot get acquainted with these steps, you will suffer for entire semester. So I will definitely put this question in the quiz. And even though I emphasize like that, you are not well prepared, then sayonara. Okay, goodbye. You take some other course. And then what you do? Of course, these steps are real step by step, but you may instantly find, but anyway. So you have this one. So this is x1. This is x sub -1. Done. Okay. You don't need integration. Got it? Especially for real valued sinusoidal functions. Use what? Use Euler's identity. So whenever you see sines and cosines, never try to use your old tools. So abandon your high school toolbox about trigonometric identities. Use your new tool based on the Euler identity. In order to derive, for example, this one, cosine 3 theta. Write it using sine and cosine thetas. How can you do that? Well, this is too artificial, but you may write it this way. Am I right? Real part of e to the j 3 theta is cosine 3 theta. Am I right? And what you do? Real part of what? E to the j theta raised to the power of 3. And then what happens? Cosine theta plus j sine theta raised to the power of 3. And then you take only the real part, and you know cosine theta cubed. And what happens? Minus. I forgot the equation, but you know how to fill up. Some 3 cosine and sine square, probably negative, right? Am I right? I'm not sure. I'm a professor, so I will just grade, even though I do not remember. So in this way, you can derive anything. For example, if you want to find some identity for cosine A plus B, where, what is that? Or you want to do some cosine A times cosine B equals something? Just try to use Euler's identity. And when you do that, probably you need this real part of something. This is very, very powerful. Got it? So you have around 2 weeks to exercise yourself. Okay? So please do so. Parseval's theorem or Parseval's relation is one of the very interesting things. What is the interpretation of this Parseval's relation? What is the interpretation? Especially for periodic signal. Of course, there are 4 versions of Parseval's relations, as you remember from the signal-gen system textbook. One is for real valued, not continuous time periodic signal. So for continuous time periodic signal, you have a Parseval's relation. For discrete time periodic signal, you have a Parseval's relation. For continuous time non-periodic signal, you have Parseval's relation. And discrete time non-periodic signal, you have Parseval's relation. What do they say? So here, I will just pick only one of the 4 things. So here you have general complex valued periodic signal. And using that period t, suppose you have found Fourier coefficients. Then the possible relation, not mathematically, but physically or in engineering sense, what does that mean? What is this one? This is called the energy of the periodic signal x of t within one period. Because this t, what does this mean? Integration interval with length t. It could start from 0 to capital, it could be 0 to t, or t to 2t, or million capital T times million 1 capital T. It can be any period t period, and we divide by the period. What is this quantity? This is the so-called power of the periodic signal x, because energy divided by its period has the unit of power, watt, okay, joules per second. And so suppose you want to compute the power of your periodic signal, whether it is a complex valued or it's a real valued signal. Now, the password relation tells you what? This power over periodic signal can be computed from the Fourier coefficients. And as far as I remember correctly, it's simply sum of magnitude squares of the Fourier coefficients. It's amazing, right? Very interesting. One of the reasons why this works is that those e to the j 2 pi kt divided by t, those functions are orthogonal within a period. So each term is the contribution of the power from the nth complex exponential signal. So the power of the periodic signal is the summation of the powers of the complex exponential signals. That is the engineering interpretation of Parseval's relation for periodic signal. You can do the same thing for discrete time periodic signal, and you can do the almost same interpretation for Parseval's relation for the continuous time non-periodic signal. So let me do that. So this is for CT periodic. Now for CT non or aperiodic. So you have x of t. So let me jump. So suppose you have the synthesis equation. And many of you, I understand, because when I was taking the introductory communications course, I also had very vague understanding of this one. See that the left-hand side is a function of time, right? Now, the right-hand side must be a function of time. Now, you have to integrate with respect to t. That doesn't make sense, because if you have dt here, the right-hand side cannot be a function of t, because t is a dummy variable. So never forget, I may put it in the quiz, okay? Probably I just make a blank here and type the character. And if you put t, then, okay. So here, actually, this must be interpreted as what? Whenever you observe some integration and hard to understand what's going on, just try to replace the integration with summation. Okay, but we don't know the parameter. But anyway, summation and f, let's say k. Forget about that dt, df. Then now suddenly those smoke disappears. And you see that, okay, the right-hand side is sum of time functions. Of course, it's a function of time. Again, function of time. So right-hand side is a function of time weighted or scaled and summed. However, if you have uncountably infinite terms, you'd better use integration instead of summation. This is the synthesis equation. Okay? Synthesis equation in Fourier transform means that given a continuous time signal x of t, it can be approximated as a summation of complex exponential time functions with weight Fourier transform. Okay, so Fourier transform must be understood as what? The weight of the component with frequency f. Got it? This is the synthesis equation. And of course, here we have a pair. X of f equals x of t e to the negative j 2 pi ft. And d what? T or f? dt. Right? Because left-hand side is a function of f. You cannot put f here. Right? And that can be interpreted as an inner product between x of t and e to the j 2 pi ft. Can be interpreted. So this analysis equation does what? You extract from x the weight or proportion of e to the j 2 pi ft with a specific frequency f. Got it? That is Fourier transform. Now, Parseval's relation for this one. Given none or a periodic signal x of t, you want to compute the energy of signal, which is defined as x of t absolute value squared dt. So you take the square integral of the signal. That is called the energy. And this energy can be computed using Fourier transform. And you have this relation. This is a Parseval's relation for non-periodic continuous time signal. Got it? So for non-periodic signal, if energy is finite, it's called an energy signal. Energy is finite and positive, actually. Energy signal has this relation. Its energy can be computed in the time domain or in the frequency domain. So we call this one as what? The energy spectral density of x of t. Because why we call it? Consider the density of mass in your physics course. What happens? If you integrate the density in some part in some interval, you have the total mass within that part. Similarly, if you integrate something on the entire frequency interval, if you get energy, you have to call it energy density. And especially, it is not a function of position, it is a function of frequency in this case. That's why we call energy spectral. Spectral means frequency density. Got it? So it is called the energy spectral density. So Parseval's relation means what? For the non-periodic signal, it relates the energy of the signal with its energy spectral density. You must interpret the Parseval's relation for a continuous time non-periodic signal in this way. Never just try to remember the equation but try to understand the meaning of the equations. And you can find a lot of Fourier coefficients and sinc functions and those things. By the way, I really love this definition. Okay. Because some textbooks, especially some math books, define sinc function without having pi inside the sign in the numerator and in the denominator. We put pi here when we define a sinc function. Some books have definition something like this. By the way, many of you, whenever you first saw sinc function, what the hell is that? Right? That was your screaming. But amazingly, if I write it differently, suddenly is your friend from your high school. And you all remember that. What? This one. So actually, your sine theta over theta was your what? Sinc function. Interesting thing is that no high school math books, as far as I remember, draw the graph of sine theta of theta as a function of theta. And it looks like that, right? Exactly what you know from the signal-gen systems. By the way, if you put pi here, this becomes 1, 2, 3. So at every non-zero integer, sinc function 0 crosses, right? And it looks like that, and you know that since you want a smooth curve, you define the value of sinc 0 as its limit, as you learned in high school. By the way, you know the university, the Ulsan University of what? National University Institute of Science and Technology, UNIST. When UNIST first established it, they haven't yet fully hired their faculty members, but had to hold their entrance exam. And many postdoc professors was paid to serve as the interviewer. And I also volunteered because they paid a lot. And amazingly, the first entrance exam to UNIST had sinc function in their exam. Of course, it was right in this way, but the problem couldn't be solved easily without drawing this curve, graph of sine theta over theta. But amazingly, many students, they never draw because they never saw the graph. Probably you cannot find the graph of sinc function from any high school math books. Am I right? Have you ever seen from 수학의 정석 or 현우진's some book? Never, right? But some students draw this curve. I was amazed. And they solved the problem just instantly. But some students just keeping this and they never solved. And I don't know whether they entered successfully and graduated or not. But anyway, time's up, and I'm still talking about signals and periodic signals. But as I told you already, even though I didn't fully cover the signal-gen systems part, your quiz covers the entire signal-gen systems. Okay, if you have any questions about the signal-gen systems material, first, you have enough time. So try to find that part from my YouTube channel, signal-gen systems. And you still cannot understand, then send me an email. Okay, I will try to reply as many of your emails as possible about any questions. Got it? However, our quiz schedule will never modify. Okay, that's all for today.